In the club. So this is all going to be important information that you'll have to refer to periodically. Some of it would be things that, depending on your level of experience, you may already know, but others you may look at and say, well, I don't know that. Well, that's why I made the table, so that you'd have that information. Like, for example, the reflexive property of congruence. We're going to use that fairly frequently. And it seems like it would be a weird thing to use as a rule. Like, of course, something is congruent to itself, but you'll see the instances in which we would use that piece of information. Right? So yeah, that's an instance where it maybe something would not be as familiar. But for example, a diameter of a circle might be very familiar to you. Right? So, but definitely use this as a reference, because even if you think you know something, you may not, or maybe you do know something, a term, you may not know it in the way that's most useful for constructing an appropriate proof. Right? So number one here, write a conclusion based on the given in each question, state the reason for your conclusion. So they're telling us that BD bisects angle ABC. Right? And so you start thinking about, okay, so what does that mean? What does that tell us? Well, if you bisect something, you cut it in half. Right? But it is an angle. Right? The ABC is an angle that's being split. All right. I don't know why I don't have all my highlighter options here. All right. Well, I guess I'm using yellow for now. All right. So the angle bisector seems to make the most sense. A ray line or line segment that divides an angle into two congruent angles. Right. So we may know of an angle bisector as being cut in half, but maybe that's not the appropriate way of writing it. Right. So the conclusion here, if it's going to get split into two congruent angles, that tells me that this angle here would be the same as this angle here, based off of that angle bisector definition. All right, this angle, really need this my different highlighter options to work. I'll just use the whole thing because we're not going to really use the Desmos or anything like that today. Right, there we go, better. This angle here is known as ABD. I'm sorry, AD. I said it right the first time. ABD, or if you say it the other way around, DBA. So that's one of the angles that's now created as being part of the congruence relation. So we would say angle ABD is going to be congruent. And it's like, well, what's it congruent to? Let me get this yellow out of here for a second. It's congruent to this angle here, CBD, or DBC, again, depending on which way you're reading it. As long as angle, the point at B is the middle of your angle. So CBD would be my other angle. These two angles are congruent to one another, and that would be by the definition of the angle bisector. Right? Since it's a known definition, it's a known term, we could rely on that information or that definition to allow us to draw the conclusion. All right. So that's in lieu of saying something like they're congruent because we know it is. Well, how do you know it is? because it's an angle bisector. Well, what about it being an angle bisector leads you to believe that that's true? It's all in the definition. Oh, well, what's the definition? Oh, that's a different conversation. But as long as you know that it's all in the definition, that's what's going to justify your conclusion, then you're good to go. It's kind of like when I would say this conclusion by modus ponens, I didn't then have to explain the meaning of modus ponens. It's all in the definition, So there are some things that we'll rely on as being the basis of logic and geometric proof. Right? So for number 2, and that's all we could do for that. I mean, there's other statements that we can make, but the main conclusion I would draw would be that ABD and CBD are congruent to one another. Right? AB bisects XY at M. Right? So what that's telling me is that AB is the bisector to XY, meaning it's the knife that's cutting XY in half. So that's telling me that these two pieces, I get my highlighter to time with my actual speaking, these two pieces are halves of the whole, right? Which would mean that they're congruent to one another. And we could use the definition of a line bisector to cover that, wherever that is. Yeah, perpendicular bisector. Oh, segment bisector, there it is. Okay. Took a sec. But the segment bisector, a line, segment, or ray that divides a segment into congruent segments. That's what happens here, or that is what is happening here. Right, so that rule would apply. So I would be saying here that XM and YM are congruent to one another. Right, and that would be the definition of the segment bisector. And that's really the only conclusion we can draw there. Right? Now, AB was the bisector of XY. It says AB bisects at XY. So take the word bisect out and replace it with cut. AB cuts XY. Cuts it where? At M. Right? So AB is the knife cutting XY. So AB didn't necessarily get split in half, but XY did. Right? Now, if they said AB and XY bisect each other, then that relationship would work in both directions. But that's not what was said here. Right? They said in number 3, AB is a perpendicular bisector of LM at J. So right above the one we just used is another one, perpendicular bisector. A line perpendicular to a segment at the segment's endpoint. Midpoint, right? But that's referring to another thing. They got into the midpoint here. Which is a point that divides a segment into congruent segments, right? So what we get from this is that we're going to get right angles and congruency here. So these two segments are going to be halves of the whole, but they're also going to combine to form a right angle with the other line segment. So we're going to get two conclusions out of this. Right? One is that AB and LM are perpendicular to one another. and also that LJ and MJ are congruent to one another. All right, and that would be definition of perpendicular bisector. Of a segment. Right. Really can't think of any other instances in which you would have a perpendicular bisector other than applying it to a segment. But that's what the title is, so that's what we write. So we're able to draw these little conclusions. And what's going to happen is when we create a rigorous proof, we're going to have multiple little mini conclusions that are all going to be part of the progression towards an ultimate goal of proof. Like, what is it that we're trying to ultimately verify or refute? All right. The focus of which is going to involve triangles in many ways. So that's the next page. We have methods for which we can prove triangles are congruent. All right, there's a bunch. Right, lots and lots of diagrams here. So it's going to take a couple minutes to mark all these up, but it's definitely worthwhile because it'll cover every possible outcome. Now, I drew generic triangles here. I mean, I didn't draw anything, but I produced generic triangles. They all look equilateral, equiangular, but they're just meant to be stand-ins for other triangles that could be congruent. So it could be, you could have triangles that look like this, but I just drew it generically, right? So when we say the Sss axiom, we're saying two triangles are congruent if three sides of one triangle are congruent to three sides of the other triangle. Right? Congruent meaning equal in measure. So what that could look like would be maybe this side is congruent to this side is congruent to this side, or this side is congruent to this side. So that's a possibility. Right. There's all sorts of different possibilities. I mean, really, I don't know that for this case, you have to really go through every possible variation. Just the idea that you'll have corresponding sides being congruent to one another is usually enough. But you could also have all three sides of a triangle be equal to each other, like within the triangle and then between the triangles. So that's another possibility. All right. But we could just take these measurements and rotate them around and just say, well, maybe these two are congruent in some way, then these two, and these two. But that's really saying the same thing. It's just labeling it somewhat differently. What that would be equivalent to is if I had triangle ABC with, like I called this ABC. Right. And then this one was DEF. So I had the same triangle. I just moved the labeling. So for example, I had A here, C here, and B here. All right, D here, E here, and F here. It's really the same scenario, but the labeling is different, right? But technically that would be a unique case, right? So we could go around and keep doing stuff like that. We could say this one is congruent to this one. This one is congruent to this one. I'm sorry, this one, and then these two are congruent.
with the one tick mark being the smallest, the double tick mark being the middle sized, and the triple tick marks being the largest one. I mean, that's another possibility. All right. You can do everything in the reverse order too. So it's like, okay, so I'm going to start off with the one being congruent to, the smallest being congruent to the smallest, middle being congruent to the middle, largest being congruent to the largest, and then work my way around that way. Right, but it's all just different ways of saying the same thing. Right. You don't really need the labels in terms of A, B, C, and all that stuff. That was really just to give you an idea of how that could play out. Right. But really, all you get at this is, as long as you have 3 pairs of corresponding congruent sides, then you have a relationship where the triangles would be congruent. If you have 2 pairs of corresponding congruent sides and the included angle is also congruent, then the triangles will be congruent as well. Okay. So that's the Sas axiom. So the way that would look is if you had, let's say this side is congruent to this side, this angle is congruent to this one, and this side is congruent to this one. That's one case. It could also be the case that maybe this side is congruent to this one, this angle is congruent to this one, and this side is congruent to this one. We don't have a third side necessary to be congruent here, because just by having the two sets of corresponding sides being congruent and the included angle, the angle on the pathway between those two sides, that's really enough for it, right? Sorry, I'm just looking for a setting. Maybe I'm not going to find it. Who knows? Yeah, I don't know. Looking for that mute function. Just do it manually. I don't know who's unmuted, but at least I can just go through. I mean, I like dogs as much as the next person, but we will see. I can't tell if I got it. Okay, well, I'll find out in a minute, I guess. All right, so it could be that it's this side congruent to this one, with this being the included angle, and these two sides being the other pair of corresponding congruent sides. All right, it could also be the same relationship, just going the other way. All right, so just flip-flop everything. All right, so start here, work your way around. All right, so having these diagrams can be useful just as a way of getting a frame of reference, because you'll look ahead and you'll see triangles that look nothing like this, but you'll see the arrangement of information that's presented will look very much like this. And so it's just a question of how does it all fit. And you'll see examples of this in a couple of minutes.
All right. Asa axiom. Two triangles are congruent if two angles on the included side are congruent to each other, right? Corresponding between two triangles. So basically, same idea as the SAS, just two angles instead of two sides, right? So that would be an example like this pair of corresponding congruent angles, this pair of corresponding congruent sides, and this pair of corresponding congruent angles. But maybe it's this pair of corresponding congruent angles with the included side, or maybe it's this pair of corresponding congruent angles with the included side. Or take all those and flip the order. All right. So if I have a pair of triangles in which the breakdown is that I have two sets of corresponding congruent angles. So one triangle or one angle in each triangle is 30 degrees, another angle in each triangle is 45 degrees. And then you know that the side that those two angles share is 5 meters. That's going to follow the ASA pattern, which would mean that those two triangles are congruent. You wouldn't need any other information. The Asa axiom would apply. Sorry, just reply. All right, so then there's the Aas axiom. So just different ways of pairing the letters A and S together, except for the bad one. Aas axiom would have two pairs of corresponding congruent angles, but with the pair of corresponding congruent sides not being contained between those two angles. So that would look something like this. I have two angles, but not this side. That one would be one that wouldn't be part of this because that would make it ASA, right? So it would either be this scenario trying to copy paste here, or this one, right? So the pair of corresponding congruent sides is not in between those two angles. It's actually opposite one of those angles, right? And in fact, we'd probably label this as a double tick mark just because it's opposite the double arc, but that's not really necessary because there's only one of them. So there's no need to distinguish it one from the other. But to be consistent with the way we've always done things, you may want to do that. So I'll do it here. So if you're wondering where the single tick mark is, there is none. All right. Now, it could also be the case that the first angle is here, the second angle is here, the third one. Really, the reason why we're able to kind of get away with this is because if you know two pairs of corresponding congruent angles, so the first pair of angles are congruent, the second pair of angles are congruent, then the third angle actually must also be congruent because they're bounded by 180 degrees. So if you know two pairs of corresponding angles are congruent within a triangle, within a pair of triangles, then you also know that the third one would be congruent as well. All right. So any pair of corresponding sides that are not between the two given angles would justify AAS. So for example, this, right? But we could also say, just like the last iteration, we could also say this. All right, there's actually 12 cases for this one, but all we would be doing is what we were doing in the last one, just reversing the order on everything. I thought that would have been a little overkill. So the last set of cases would be if you have a pair of corresponding congruent angles, and let's say these two sides are congruent, but you could also have a pair of corresponding congruent angles where these two sides are congruent. All right. Now, if it happens that the pair of sides that are congruent are between the two angles, that doesn't mean the triangles aren't congruent. It just means they're not congruent. You can't say they're congruent by the Aas axiom. They would be congruent by the Asa axiom. All right. So they're congruent. It's just a matter of why they're congruent. And then you have a special case, which is the hypotenuse-like theorem. Two right triangles have a congruent hypotenuse and corresponding congruent leg or congruent triangles. So for example, if I know the hypotenuses are congruent and I have a pair of corresponding congruent legs, then the two triangles are congruent. So that's one instance. And here's another. All right, but that's really the only kind of breakdown that you could have for that sort of thing. So you kind of root for right triangle situations because those are the easiest ones, right? But they're the most infrequent ones, so they're the easiest ones to forget. Right? But that's why I have this page in your packet for you, so that in theory you can quote unquote easily reference the different possible cases and use that to help draw your conclusions. Conclusion being the word of the day. All right, conclusion. All right. So we are drawing conclusions in this lesson. So it makes sense that I would make conclusion the word of the day. And actually, this lesson is the conclusion of this topic. So it makes it even more interesting. All right, so we have our examples here. Like I said, they're all like little different flavors compared to what you see up here. These are all the generic cases. But what I'm looking at in the first example is a pair of corresponding congruent angles, right? And it's surrounded by two sides that are corresponding and congruent. So this one is congruent to this one, and this one is congruent to this one. All right, so I would look for the pattern. If I don't have an intuitive understanding yet, I would look for a pattern that kind of feels like that. All right, so first I'd be looking for a pattern that only has one angle in it. All right, so that's leading me to the Sas axiom area. And then I would be looking for any instance where I have two pairs of corresponding congruent sides, right? So that looks an awful lot like this case. Right, just the shape of the triangle is somewhat different, but it's got the same breakdown. Right, so we have a match. That's an Sas axiom situation. So we can now say that those two triangles are congruent, but they're specifically congruent by the Sas axiom. Those kind of situations are sort of nice because I don't want to say they're tailor-made because it's not perfect, but it's pretty close. So it's pretty nice the way that works out. It's when you get to the numbers 2, 3, and 4 where things get a little dicey, because you look at this and say, well, number 2 is not a triangle. It's actually two triangles that are sharing a side. Right? So
what I would want to do is at least consider what this would look like if there were two separate triangles. Right? So basically, I'm going to take this triangle here. That's DEF. I'm sorry, DEF. DCF. And I'm going to pull it out of the picture here. And if I could resize it and change things up, I'm sorry, not resize it, rotate it without changing its size, I would. But it's not going to look pretty. But what I can do is keep the markings. Right. So I have this one with one tick mark, this one with one tick mark. That X is a way of representing the reflexive property. That's the one that says a side is congruent to itself. And it seemed like the weirdest thing, but it's basically saying that if you have a side in one triangle that is also a side in the other triangle, it's congruent to itself because it's acting as two separate sides, the side of one triangle and the side of the other, right? So I would be looking at this one. Oh, the song took a turn. So here's my DEF. Oh, I used a way thicker marker there. Hold on. At the end of the day, it's nighttime. It's not going to be that big of a deal. I just want to fix it. All right. So if I pull it apart, you see here, I'm still looking at side DF and side DF. It's the same side, right? So there would be congruence there. So you could still use the X if you want, but now I can actually say that this is a double tick mark, right? So I'm looking at an SAS arrangement. You know, it's kind of harder to see at first glance, but if we look carefully, we can see that the top triangle matches the one over here. Right? These are the, oh, that just jumped on me. I don't know what happened there. All right. These are that's basically the same arrangement. And you say, well, what about the bottom one? Well, it's just a rotated version of it. All right. So if I were to let me duplicate it because I don't want to lose the sizing. But let me try to show you. If I take it and rotate it while maintaining its size, I'd end up with something that looks like this, roughly, which in theory should match up with the other triangle. But you see, I lost the size relationship in rotating it. So it'll never look the same, but, or at least not using this app. But this triangle here rotated should be the same as this one. Right, that got a little closer anyway, but that's the idea. Right. Bottom line is I have two sides and an angle included between the two, which means that these two triangles are congruent by SAS. Right. Although looks like our first typo of the day, well, first real one, I'm sure there are other ones. I don't know what I was referring to. I know I chopped this lesson up from a previous version and I removed some examples. This is probably referring to something else, obviously. This should say triangle DEF is congruent to triangle, well, DEF CDF. right? And that would be by the Sss axiom. All right, so in a lot of ways, it's really just a matter of pulling the two triangles apart from wherever they're connected and going from there and seeing what the relationship is. All right, so I'll do the same thing with the next one. We have a parallelogram, or at least it looks like one. It's asking us to prove that those two triangles indicated are congruent, but that's also an error. So we'll get rid of that. This would be triangle ABD congruent to triangle CDB. All right. So if I draw this triangle, label it up, so I have D, C, B. I have my double arcs here, and that's really all I have, except for that reflexive side. I have that. I can hang on to that. I'm just going to move this over here for a sec. I'm going to shrink it all down in a minute, but I want to draw the other one first. So A, B, D with the double arc here. So these are what the triangles would look like if you pulled them apart. But like I said, I'm going to shrink them down. I just wanted to shrink them down together so that the size relationship would remain consistent. This is kind of like a window into the world of this scenario. Right. So we have that reflexive side. Right. Oh, and it looks like I missed a couple of arcs. Right. So this one should have a single arc, and this one should have a single arc. All right. The reflexive side tells me that this distance here is going to be the same as that one. So these two sides are congruent to one another. So I'll just put a little single tick mark there. All right. So what I'm looking at is an angle, a pair of corresponding congruent angles, another angle, another pair of corresponding congruent angles, and then the included side. Right. And again, what we mean by included, in fact, if you take the word included out and say on the path to, that might be a better way of thinking about it, because the side that's on the path to the other angle. So from one angle, following the path to the other angle, that would be the included side. That's what that's known as, right? So this is an ASA arrangement, right? We could find a diagram that looks like that. That would be, I mean, it's pretty crappy, but that's going to be pretty much this one. So we had this one before. Actually, let me make this look a little nicer. All right, but this one is going to be the Asa Axiom. Ooh, a little small now. All right. So as long as you know that you can rotate the figures and still end up with the same arrangement, you'll be in good shape. All right. So that's what's happening here. Again, like I said before, I can't rotate with this app. I can't rotate a diagram without also resizing it. So you lose a little something in that, but just carefully doing the best I can to try to maintain its size if I rotate it so that it has a similar orientation to the other one, the other triangle, it's a little easier to see that they're congruent. So something like that. But like I said, it's kind of hard to get it to match up because it keeps resizing on me. Right. So that's the idea. Right. They would still have that apples to apples relationship. It's just it'll look a little different. The last one in this little section before we get to an actual proof is a rectangle. Now, again, we're looking at everything from the perspective of triangles. And the reason why we do that is because triangles are the basis of all other geometric figures. Right? You can decompose any other geometric figure, even a circle, into triangles. So if you learn everything there is to learn about triangles, then you'll learn everything there is to learn about other geometric figures. Oops, that's not my lasso. All right, so there is my two, or there are my two disconnected triangles now, just maintaining the same labeling. We have LMN, LNO. We have right angles here and here. The hypotenuses are equal to one another in length, which means they're congruent to one another. Right. Shockingly, this statement here is correct. Right. We have a pair of corresponding congruent legs. So the hypotenuses are congruent and the pair of corresponding legs are congruent, which means that these two triangles are congruent by the hypotenuse-like theorem. Right, which most people abbreviate H-L theorem. Right. So far we've kind of built our way through the basics, or I guess navigated our way through the basics of constructing a proof by drawing little conclusions related to line segments and angles, and now little beefier conclusions related to sides. Sides, angles, and triangles. So now it's time to kind of put it all together. So in number 5, they say given ABC, triangle ABC, with AC congruent to BC. All right, so the first thing I'm going to do anytime I see some given is I'm going to label up my triangle. Right, it makes sense from a visual standpoint, but also from a matching it up to an SAS, ASA, SSS rule kind of standpoint. Right, so it's nice to know the manifestation of the statement that they're giving you, but it's also nice to see how that correlates to other things that that we have as reference material. Right, so they're telling us that side AC is congruent to BC. So that's this side here. AC, BC. CD bisects angle BCA. So BCA is, I highlight that, I'll do that in yellow. BCA starts off at B, goes to C, and then travels on down to A. It's saying CD is the knife that cuts that angle in half. If it's cut in half, it's cut into 2 equal pieces, which means that these two angles are congruent to one another, one arc only necessary. All right. So what we need to do is prove that these two triangles are congruent, right? So we need statements, we need reasons. Sometimes a statement is just a given, which is really nice. Right, so all of my given statements are part of my proof. So
this is, they call it a 2-column proof. It's just another organizational strategy. It's very popular in geometry classes because proofs, geometric proofs, can be very disorganized and hard to parse through. You could have two wildly looking, different looking proofs that are both correct. And it's kind of hard for the reader to be able to navigate their way through the thinkings of the individual constructing the proof unless there's some sort of required structure. So that's why we ask you to do statements and readings. Right. So the first statement would be that we have some sort of triangle ABC. For some reason, I decided to let that triangle symbol be the A. No, triangle ABC with AB congruent to BC. Right. So you get your given statements in there. We had another given statement, CD bisects angle BCA. Both of these are givens. All right. After that, we start drawing conclusions. All right. So this is like a logic proof where they tell us, I'm wearing a red shirt. I am wearing blue shorts. If I am wearing a red shirt, then I am wearing blue shorts. Like prove that I'm wearing the blue shorts. You know, like you have some given information that you could put in symbolic form, or you could leave it. I mean, if you wanted to write out the entire sentences, you could, but it wasn't really practical when it came to logic. But here it's not that bad because we have some understood symbolic notation. All right. But if I'm going to prove that these two triangles are congruent, just looking at what we have here, I got a triangle here. I'm going to pull that out. And I have another triangle here. It looks like I don't quite have enough yet to say that they're congruent to one another. You know, we're close, but we're not quite there. There's one piece of information that we would need in order to prove that these two triangles are congruent. It has to do with how you prove triangles are congruent in general. And that is by the axioms. All right. So I need either all three sides to be congruent from one triangle to another, 3 pairs of corresponding congruent sides. All right. It doesn't look like I'm close to having that. I could have 2 sets of corresponding congruent angles, which I'm kind of close to. If this were a right angle, then I'd be in good shape, but they didn't say that, so I can't assume it. Right? Just because it looks like it doesn't mean it is. I mean, it could be an 89-degree angle, and the other one could be 91, indistinguishable from, you know, just at first glance from a 90-degree angle, so we can't make that assumption. But we could also try to apply the SAS, but if I do that, I would need another side. So labeling helps, because if I label this ADC and BDC, it might just kind of pop out at you, oh, wait a minute, these two are the same. DC, it's the same line segment. Right? And that's because CD is a reflexive side. Right? So I could say, as weird as it is to make the statement, CD is congruent to CD by the reflexive property. Now, we have the information to prove the two triangles are congruent. You just look at the picture. But we don't have the justification yet, right? Because nowhere in my proof did I say that these two angles are congruent to one another. Right? I said it in my picture, but I didn't say it in my proof. In my proof, it says CD bisects BCA. And this is what, when people struggle with proofs, this is what they struggle with. They're like,
Well, I know that because it says it right there. It doesn't say it explicitly, right? You got to spell it out, right? And what spelling it out means, you're applying a definition. So angle ACD is going to be congruent to angle BCD. And that's the definition of angle bisector. All right. So they explicitly said that AB. Oh, sorry, I wrote that incorrectly. I wrote AB is congruent to BC. I meant AC. They explicitly said that AC and BC are congruent. I explicitly said that CD is congruent to CD. I explicitly said that ACD and BCD are congruent. So now we have explicit justification that two pairs of corresponding congruent sides and their included angle are congruent. Right? So if you kind of look at this and compare it to one of the diagrams, you know, because it's sort of an acquired taste when it comes to proofs, you know, being able to recognize these things on site. But if I'm looking at this, I see this arrangement here. One tick mark, one arc, two tick marks. I mean, it's not perfect, but it does follow this pattern. One tick mark, one arc, two tick marks. Right? So we have it. It's just the triangles don't really look the same, but they don't have to look the same. These are generic cases. Those are particular cases, right? So we can now say that those two triangles are congruent by the Asa axiom. So my last and final here would be triangle ACD congruent to triangle BCD by the Asa axiom. So number 6, DB bisects CA. See how it all kind of comes together? It's all part of the master plan. DB bisects CA. So CA is the one that's getting cut in half. DB is the one that's doing the cutting. So DB bisects CA. All right. Now from that, I can now say that CA is split into two equal pieces. Right? And those two equal pieces have to be congruent. So that means, so this is my given, that AE has to be congruent to CE. And we'll get to the justification on that in a sec, right? But hint, it's in the statement. So bisect is going to be in there somewhere, right? They also flat out told us that D and B are congruent to one another. Right. So my second given here would be angle D is congruent to angle B. Now, normally we name angles with 3 letters. This time we could get away with only 1 because there's no other possible angle that that D or B could be, pun intended. So there's no confusion as to what I'm talking about when I say angle D or angle B. So I have one pair of corresponding congruent angles and one pair of corresponding congruent sides, right? Now to get the justification for the pair of corresponding congruent sides, I would talk about the definition of segment bisector. All right, so we just need one more either side or angle. It would be great if they said, well, actually, it wouldn't even help us, but it would be more information if they said D, B, and CA bisected each other, but they didn't say that. All right, but I do have some vertical angles here. And if you remember from last week, these two angles have to be congruent to one another because they're vertical angles. When we talk about parallel lines and transversals and alternate interior angles along the way, we talked about vertical angles. If you have an angle of two line segments that form an X, the opposite angles in the X are vertical angles, and those angles are congruent. All right. So it's going to be a little bit more of an elaborate statement, but I can now say that DEA, angle DEA, is congruent to angle BEC. All right. And that's because DEA and BEC are vertical angles, and vertical angles are congruent. So I took two disparate ideas here and put them together using a conjunction and. You could always do that when it comes to a proof as long as both parts are known to be true. All right, as long as you've justified or you have a justification for those two statements within the conjunction being true, then you're good to go. So I'm doing a 2-for-1 here by saying DEA and BEC are congruent because they're vertical, but also their vertical angles are congruent. True and true is equal to true, so I have a logical basis for my argument. All right. Now I have two angles and a side, but that side is not included between the two angles. All right. That's the definition. Well, everything's a definition, right? That is a case in point of the Aas axiom. So triangle AED would be congruent to triangle CEB. And that's the Aas axiom. And again, that's because the side that's given is not included between the two angles. Right? If it was in between the two angles, even better. Or even the same. Because it would still be a case where the two triangles are congruent. It would just be based off of the Asa axiom. Right? So we don't make any statements without an appropriate reason based in geometry or logic. So far, the logic really hasn't been necessary, except for the one little thing I addressed with conjunctions, because none of these have been really substantially conditional, except to say that if all of this is true, then this is true. So I could look at this as P, Q, R, S, and T, and I would be, this is really the same as saying if P and Q and R and S are true, then T follows. But that's covered in, I don't want to make this too busy of an example, but that's all covered in the 2-column proof aspect of it, right? Because every time I make a statement the way it's structured, it's that 1, 2, 3, 4, it's all in conjunction with one another. 1 and 2. Now add in statement 3. Now add in statement 4. We're building on our argument. This is true, and that is true, and that is true, and that is true. Therefore, this must be true. All right. So again, we're still proving triangles are congruent, but now they're giving us a perpendicular relationship in number 7. All right. Perpendicular lines form right angles, and those right angles are congruent to one another. All right. But before we get there, might as well get our givens in there. AB perpendicular to CD, and CD bisects ACB. And my handwriting is taking a turn. All right, so both of these are given. We want to be thinking about what this all means, right? Like I said, AB being perpendicular to CD means that we're forming 2 right angles, right? That means that this is a right angle and this is a right angle. Well, if they're both 90 degrees, then they're both going to be congruent to one another. So I have one pair of corresponding congruent angles now. Get this to fit somewhat. So that's good news. Now this could go down one of 2 pathways. Because I'm looking at a right angle, it could be a hypotenuse-like situation because I have a right triangle. But it could also just be a simple SAS, ASA kind of deal, where I have multiple angles congruent to one another, right? It seems to be leaning that way because of the second statement, CD bisects angle ACB. Right, ACB is right up over here. That's the one that's getting cut in half and therefore congruent. Right. Now we also have a reflexive side. Right, CD is congruent to itself. Right, ADC, BDC. Each triangle has a side DC. They're the same DC, so I have congruence there. Now I haven't justified any of this congruence, but it's all there. We have it in the diagram. We have a roadmap for our proof. We just need to elucidate. Right now, memory is a powerful tool. Sometimes, I mean, the more experience you get with some of this stuff, you start realizing, oh, I've done this before. Right. So I vaguely remember doing something with an angle bisector already. CD bisects angle BCA. Yeah, that was great. That was the definition of angle bisector. We did the exact same thing over here. Right. It's just a labeling. Was the labeling different? ACB, ACB with the D on the bottom. No, the labeling was the same. So we can just snag this bad boy right out of here. And actually, the reflexive property is the same too. I could take that also. I'm going to get a little greedy here. Same picture. You're asked to do something slightly different with it, but ultimately it's the same thing. So I have reflexive property and definition of angle bisector. So that gets me most of the way there. I haven't addressed the congruence of angle ADC. Right, we have ACD and BCD, but I need angle ADC and angle BDC. We know they are congruent because it's in the picture. Look at that. It's labeled. They both have 90-degree angles. But it's in the picture is not going to
cut it as a justification. Justification being the second word of the day. Justification. Seem to be talking about that a lot. So it makes sense to incorporate that into our conversation. Justification, second word of the day. All right, so here we're talking about a perpendicular line, perpendicular relationship. Now, we could say perpendicular relationship creates congruent angles, but it's actually more than that. They're both 90-degree angles. So if we want to be as specific as possible, we could say perpendicular lines create congruent 90-degree angles. But you could also look up in our definitions to see if there's anything that could be helpful, like perpendicular intersecting lines to form 90-degree angles. So if we know that they're both 90-degree angles, then they must be congruent. So we'll take that idea, build upon it, and we'll have our reason for stating that these two angles are congruent to one another. All right. So perpendicular lines. So I'm going to put the definition rather than the title of the definition. Perpendicular form 90-degree angles, and this is a weird one to say, but we have to justify the congruence, right? Yeah, we stated that they're 90-degree angles, but we never said anything about congruence. So all 90-degree angles are congruent. Right. So instead of, because, and really, I mean, this is the line of demarcation in terms of, like where it's easy and where it becomes a little more challenging. If you have this as a rule of thumb, where if the title of the definition covers exactly what you need to justify the statement, then you just put the title. If it doesn't, and you need to amend it with a conjunction, then you write the actual definition and then include the conjunction, because you wouldn't want to say definition of perpendicular lines and also all 90-degree angles are congruent, because that's just it doesn't flow. We're looking for something that actually flows. Sorry. Took a sip of water, went down the wrong pipe. Mm-hmm. So now I have enough to say that the two triangles are congruent. That's triangle DAC. I could say ADC, but they said ADC. So I'm sorry, DAC. So I want to say what they said. So triangle DAC is congruent to triangle DBC. And that's by the Asa Axiom. Right. So every statement gets a reason. One of those reasons is going to come from the table in some capacity. It's just a question of how. Right. Now, if you know two triangles are congruent, then you know that their corresponding parts also have to be congruent, right? So I'll just take this one that we just did real quick. So now that we've gone through this proof, when you prove something, it's now 100% accurate. There's no doubt, right? So now I could go through and I'll say, all right, well, now I really know that these two triangles are congruent. Okay. That means that this side is congruent to this one is congruent to this one, this angle here. This side is congruent to this one. And we already knew that the reflexive side was congruent. So we can kind of sort of fill in the rest of the puzzle based off of the fact that we know that those two triangles are identical. They're the same. Yeah, they're facing different directions, but they're the same triangle, right? That principle is known as we abbreviated Cpctc.
corresponding parts of congruent triangles are congruent. It's basically just a simple, well, relatively simple way of saying that if you know that the two triangles are congruent, then every aspect of each triangle is congruent to every aspect of the other triangle. So, long story short, what we need to do in each of these cases, because you see number 1 and number 2, they both have us proving something other than the two triangles are congruent, right? But in order to prove that those two parts are congruent, we should prove that the two triangles that they're part of are congruent first, right? So looking at number 1, I have my statements, my givens, AE bisects angle BAC. That's one given. It's a statement, but it's also a given. And AB is congruent to AC. That's another given. So if AE bisects angle BAC, here's BAC, starting here, going here, ending here. So it's the angle at A. That's the one that's getting cut in half. That means that these two angles are congruent to one another. All right, so let me address that first. Angle BAD is congruent to angle CAD. And that's covered by the definition of angle bisector, right? It's an angle that's getting bisected, so we would say angle bisector. Reasonable abbreviations are okay, as long as it's pretty obvious what you're abbreviating. Right, so if you write def, I don't think you mean, oh, probably shouldn't use that word. Deferential, you know, I'm pretty sure you mean definition, so, you know, it's okay. Yeah, so definition of angle bisector covers that. AB and AC are explicitly stated to be congruent to one another. So boom and shakalaka. Now I just need one more pair of corresponding congruent sides or angles from this and I'll have it. Right. So again, I like to split up my triangle, but eventually, or split up my diagram into different triangles. But eventually you get to a point where you realize, you know what? I can just kind of see it as is. I don't have to draw them separately. And if you get to that point, then you're in a good spot. But until you get there, you know, it takes a little doing. So I have two separate triangles now. ADC, ADB. Hey, look, both of them have an AD in it. So that means that I have another pair of corresponding congruent sides. AD is congruent to AD by the reflexive property. All right, so now just to recap, I know that these two angles are congruent. I know that these two sides are congruent. This seems to have a side angle side formation, two sides and an included angle. So I can now say that the triangles that they're part of, triangle BAD, would be congruent to triangle CAD. And that would be by the Asa axiom. All right, so then the only thing that's left to do is, you know, actually answer the question that they asked. Because it's, you know, if you're looking at this, you might be like, well, this is all wonderful. Are you planning on answering the question? Well, now that I know that the two triangles are congruent, I know that every aspect of the black triangle is congruent to every aspect of the red triangle, right? The parts that correspond to one another. So for example, these two angles would be congruent. We get a fresh new color in here. Let's say nice green here.
these two sides are congruent to one another. Well, actually, those should have one tick mark. And then these two angles would be congruent, but let me get two tick marks on this one. Make it look a little bit more consistent. These two angles would be congruent to one another. Actually, I get my tick mark game out of whack here. They should have three tick marks. So 3 arcs.
Could I ask a question?
Sure.
Is it okay? So I know what you're doing now, I understand, but if we're doing this proof below, can we stop labeling at the point of our last, you know, whatever it might be, or should we always go back and put all the things that are congruent?
Oh, no, you can stop. You can label only as much as you need. I'm
Okay.
only doing this to justify or explain the concept of Cpctc.
Okay, perfect. Thank you.
No problem. All right, but along the way, hopefully you recognize that now we can say that angle 1 and angle 2 are congruent to one another, because those are the part of the corresponding parts of the figure. These two angles occupy the same position within the different triangles. All right, so they labeled it angle 1 and angle 2. We can't just go into a triangle and say, I'm going to call you angle 1 and you angle 2. They did it, so we have license to use it. But we can now say that those two angles are congruent by the Cpctc property, but we just say Cpctc. And that would be our complete proof. Now, the second example here ties together what we were talking about last week with the parallel lines. It says IH is parallel to LK. And that's useful information. It just doesn't seem like it would be at first, but I'll get it in there. So that is a given. And IL bisects HK, also a given. All right. So IL is the knife that cuts HK in half or into two congruent pieces. So we can now conclude that HJ and KJ are congruent to one another. All right. So HJ is congruent to KJ, and that would be by definition of segment bisector. All right, so we have a justification for that, but ultimately I have to prove that IJ and LJ are congruent. It doesn't seem like we have anywhere near that kind of information, except when you think about two pieces of critical information, both coming from last week, one involving parallel lines and the other involving vertical angles. IJH has to be congruent to LJK. So angle IJH is congruent to angle LJK. All right, so that's this pair of angles. I'll give it 2 tick marks or 2 arcs. All right. And that's the explanation we're talking about before, where the angles are vertical and vertical angles are congruent. All right, the angles are vertical and vertical angles are congruent. So I just need one more piece of information to prove the triangles are congruent. And that's where the parallel line relationship is going to come into play. All right, so It's just kind of hard to see. I mean, on many levels, diagram wise, but also just by the nature of the structure. But if we imagined that these line segments were part of a bigger diagram, right, where you had two actual parallel lines, that were cut by a transversal, and it might be a little easier to see. All right, so these are my two parallel lines. And well, the relevant transversal could be whatever you want it to be. But let's say, for example, because there's two possibilities is what I'm getting at. But let's say, for example, it's this one. If I get it to lock in. I'd have two parallel lines cut by this transversal. My tendency would be to just kind of ignore all the information, all the other information, but it's kind of hard to do that because it's sort of busy, the diagram. So I'll pull this information out and just look at it separately. Almost like a problem from last week where they would say, all right, if you know that there are two parallel lines cut by a transversal, and you know this angle is whatever, what's that angle going to be? All right. Well, we know things about consecutive interior angles, alternate interior angles, alternate exterior angles. So I can look at this and say, but it actually even simpler than that. We learned as a sight recognition, if the angles look like they're the same size, they are. Okay, but ultimately, all of these angles are going to be congruent, and all of these angles are going to be congruent. It's just a matter of justification. Within each cluster, you have opposite angles congruent to one another, and then the relationship carries over to the other cluster. All right, so then what we do is we connect that to what we have over here, and you see I have this angle here, which corresponds to this angle here, and this angle, which corresponds to this one, they would end up being congruent. It's really just a matter of justifying why on earth they're congruent, right? They're on opposite sides of a transversal, so they're alternate, and they're between the parallel lines, so they're interior, right? So I can now say that Hij, angle Hij, is congruent to angle KLJ, and that's because it's a lengthy reason, but if two parallel lines are cut by a transversal, the alternate interior angles are congruent. All right. So now I have enough to say that those two triangles that they were part of are congruent, because I have two angles and a non-included side. So I can now say that triangle Hij is congruent to triangle KLJ. And that's the Aas axiom. And then finally, at long last, the relevant parts that I was looking to prove are congruent, Ij and Lj, those are parts of the two congruent triangles. So I can finally say that Ij is congruent to Lj, and that would be by Cpctc. corresponding parts of congruent triangles are congruent. Right. So that's the lesson. You know, it was a two-parter, but that should set you up for the assignment. And just to kind of remind you about that, I'll take you over to Blackboard now. Stop recording.